video that ties in what we were talking about on YouTube Live for the predator-prey system and uses the resources that are online. Now, remember when we were working with the system algebraically and we factored out the n from this equation, we factored out the p from this equation, and we set it equal to 0 so that we could locate the fixed points? So we're going to be learning more about that next week in section 3.4. It's probably a good idea to get started a little bit this week in context to make it easier to digest next week. And so what I did here was I opened up Desmos. Desmos is going to be a really helpful tool as well. And on Desmos, I plotted what you will know next week as the nullclines. The equations I had on the board on the YouTube Live were here. Remember when we set the first equation equal to 0, we got that the prey is either equal to 0 or the predator is equal to R over A. And then the second choice was, if when we set the predator equation equal to 0, either the predator species is equal to 0 or the prey is equal to M over BA. When I was doing that live video, I was kind of talking about it in terms of a prefix menu where you choose one appetizer and one main course. So remember that these two equations that came out of setting the first differential equation, dn dt equal to 0, these two equations are like your appetizer. You either choose this red curve or you choose that one. You can't have them both. And then these two blue curves that came out of setting the dp dt equation equal to 0 are your two choices for your main dish. Either you're going to choose this blue line or you're going to choose this blue line. So that's why I chose two red. These are the appetizers. They came out of setting the prey equation equals 0. And then we have two blue, and those are the main dish, the predator equal to 0. So when you plot them on a grid like this, you can see on Desmos that we're going to be looking for places in the plane here where these lines intersect with one blue and one red line intersecting. So you can see that 0, 0 was the first obvious choice here. If we choose this equation for our appetizer and this equation for our main dish, we come upon this fixed point right here, 0, 0. And then you all in the live polls named the other equilibrium point, which is that we're going to choose this one for the appetizer and this one for the main dish. And then we get this point right here, which is the non-zero fixed point. That's located at about 100 over 3, 40. And that is the second fixed point. Now, we all got a little confused in the YouTube Live, and there was a good learning lesson inside that, which is that we thought there was supposed to be 4, because you can choose, there's 4 different ways you can play it. But if you look carefully, the other two intersections, which are here and down here, do not count as equilibria points because they are not an intersection between one red and one blue. You can see that this fixed point down here, well, it's not a fixed point. It's not an equilibrium because there's two blue intersecting, not one red and one blue. And likewise over here, there is an intersection of two lines, but they're both red. We can't have just two appetizers. We can't pick just two main dishes. We have to pick one of each or one of each down there. So now I want to show you how locating the equilibria here using this Desmos trick aligns with the vector field that you see right here when you've typed it into the online vector field plotter. You see, in this vector field, I can clearly see that there seems to be a little middle point right there in the swirlies. And that middle point, as I hover my hand, it's acting a little weird. Hold on a second. Maybe it needs to be a little bigger. Okay, so sorry about that. As I hover my cursor over this picture, you can see that the center of all the swirling in the vector field is located, keep your eyes down here when I have my cursor right there. It's located at the value around 33.3 and approximately 40. That's the same fixed point that we just found over here on Desmos. You see? The actual theoretically predicted equilibrium point, sorry, I keep saying fixed point, is 33.3333. Really, it's 100 over 3, 40. And then when I go over to this resource here and I hover my cursor where I think there's an equilibrium point, I can see that it says it's around the same place. So that's one of the fixed points. And the other equilibrium point here is 0, 0, but there's, you know, not a lot of action going on down there. Remember when we talked about what equilibrium solutions look like in a time graph? I want to show you how to illustrate that on the online tools. So the first online tool of Desmos allows me to visualize where that equilibrium point is going to be. Again, it's located at 100 divided by 3, 40. Then if I go over here to this system, which is the solver, and I type the fixed point in, the equilibrium point, 100 over 3 for the prey, and then 40 for the predator, and I click submit on that, hey, where did it go? Oh, it's so tiny you can't even see it there. There would be, if I was able to zoom in, there would be a tiny little dot right there that illustrated the trajectory, but it's kind of not visible. However, if I open up the time plot here, oh look, it even says equilibrium point. How magical is that? You can see that equilibrium points are horizontal lines in a time series. You see, they don't change at all. Their derivative is always 0. And actually, when I put my cursor over the time series, you can see the black dot that appears right where that equilibrium point is. Okay? The same thing would happen if I had typed the other equilibrium point in 0, 0 and submitted that. You see that? And it predicts 0, 0 for all time. Okay, so that's what Equilibria look like. Remember when we made that mistake and we thought maybe we could mix and match the other way? So maybe we could put a 0 there and a 40 there? If I solve that out, you can see that one of the things is in equilibrium, but the other thing is not in equilibrium. And that's what I was trying to say when I was like, nope, if we pick 0, 40, that would be like picking 2 appetizers. So the red one, the X, is in equilibrium, but the Y, the predator, is not in equilibrium. And the same thing happens if you try to type in 100 over 3, 0. That's another mix and match point where we chose both of the main dishes instead of one from appetizer and one from main dish. And so you can see that the predator is in equilibrium, but the prey is not in equilibrium. So that's why those two combinations are not fixed points. We can see that at least one of the variables does not have a straight line behavior on the numerical solution. And also we can see over here in the Desmos graph that the two things that I just typed in are not intersections of one red and one blue. It's either 2 blue or 2 red. And so those are not equilibrium points. Hope that clears up some of the confusion. And again, it's always good to make mistakes because that's where we do some of our deepest learning.